All right. So, using that picture, which we'll start with, our job today is to locate ourselves in this patch going from the inertial frame through ECEF, capital E, little e, longitude, latitude, vehicle carried vertical to the body axis. And now we're interested just in this last attitude matrix, that attitude matrix which we call the definition of situational awareness. And the first job is to define heading. So we're going to define the common vector, draw a diagram and project from old onto new for the heading task. And the common vector between the north tabletop and that airplane on the tabletop, what would be the common vector? K again, yeah? So it'd be KV. So, if I were to draw the horizontal plane, I'm going to look down on the horizontal plane. So this is the looking down on the horizontal plane, and I'm going to say this direction is north. And that, I know IV, the vehicle carried vertical I vector is north. Okay? That means that the JV vector is what? JV vector must be equal to what? So I'm looking down. JV must be east, yes, east. And KB is into the board like so, into the board. We're looking down on it. I'm looking down on the tabletop. All right, now, my airplane is pointing on the tabletop a heading side. It's pointing a heading side, and I would like to call that IB, but IB is allowed to come out of the tabletop. So I'm going to define an intermediate coordinate system. I'm going to define one, just called 2. You could think of it as IB right now, but IB eventually is going to move again. So right now we're just going to define I2, and I2 will stay in the horizontal plane. So this is going to be in the horizontal plane, always. It's going to always be in the horizontal plane. So similarly, then there'll be a J2 vector, and that also is going to be in the horizontal plane, always. And that's going to be heading side as well. Okay, I'm done with step 2. And my step 3 is to, now what? Is to project to hold on to the new, right? So I'm defining C into 2 from V, right? And I'm looking at the first row. Is that too low? Can you guys still see this thing? I don't want to go too much lower. So if I were to lay, that's why I gave you guys pens. So now you all have pens. So take these pens I gave you so you remember what they're for. These are fingers to lay along new vectors. So take your pen, lay it along the new vector, I2, and drop perpendiculars from the old vectors. So I lay my finger along I2, I drop perpendiculars from the old vectors. The first one is IB. So I'll drop a perpendicular for IB onto the new I2, like so. So I'm interested in this distance right here, and I can see right away that's going to be what? The cosine of psi. Yeah? That's going to be cosine of psi. The next element, I'm going to drop, again, I put my finger along the new vector. I'm going to drop it from JV. So I'll drop a perpendicular from JV. That means I want this distance over here. This also is angle psi, right, perpendicular lines. So now I'm going to want the sine of psi. I want the sine of psi as my second element, like so. Third element is my new I2. K is into the board, the old K. Therefore, the third one is going to be 0. It's going to be 0. And I've got my first row. Okay. Second row, I'm going to take my finger now, and instead of laying it along I, I'm going to lay it along J. Lay my finger along J, project the old vectors onto it. The old IV projected onto J. Whoops, looks like I'm going to have to go backwards again. So J is going to have to drop backwards. I'm going on the back side, so therefore, on the back side, this is going to be negative. And again, this angle over here is going to be the heading angle, my perpendiculars. So this is going to be minus the sine psi located in that element over there. Okay. If I drop the old JV onto the J2, JV, J2, I'm going to get the cosine again. And the third one, K is into the board, is going to be 0. The last one now, you should be up with me. The last vector, I'm going to lay my finger along KV, which is into the board, going into the board. It's going to align with K2. K2 and KV are aligned. Therefore, there's no projection from the old I and J vectors, and a perfect projection of 1 out for that one. And there you have the first coordinate transformation. So over here, again, after you define the 2 system, you'll rotate about the J2 vector, and the I2 axis will rotate up angle theta and become the IV vector, like so. So the airplane, from its heading position, will rotate about its right wing right now, because it's in the horizontal plane. It'll rotate up and become IV like so. Theta. So we'll define another intermediate position. We'll define an intermediate position called 3, maybe, off that, and we'll follow the 3-step process and see where it takes us in this case. Okay? All right, so first step, what's the common vector? If I'm going to define system 3, the 3 system is a rotation about J2. So J2 and J3 will be the same. Right? So if I want to find C into 3 from 2, the common vector is what? What is the common vector into 3 from 2? J2 and J3 are the same, yes? All right, now I'm going to skip a little bit. Since J2 and J3 are the same, that means that J2 is going to project onto J3, and all these are going to be zeros. Kind of like tic-tac-toe, isn't it? Right? Because all the other I's and J's have to, any I's and K's have to project as 90 degrees. So the only place you're going to have J2 and J3 is here. Every other place will be 0. So let's draw the picture just to make sure that that's the case. So in the picture, here is I2. That's in the horizontal plane, remember? So this is in the horizontal plane. Horizontal plane. And then now I've got J2 and J3 are coming out at you, okay? So this is a point. I should have put maybe K going into the board as an X, so it's going in. So J2 equals J3 is coming out at you. Or is it, let's see, J2. Yeah, and then you're going to rotate about J. So where does K go? K is going to go from K2. K is going to go from K2, and it's going to rotate through theta to a new K vector, K3. So if I were to do that, like I did the last one, then rotating about J would give me an I3 vector through angle theta, like so. And this we call pitch angle. Psi was called heading angle. And of course, K is also going to rotate. It's going to be 90 degrees from the I3 vector. And K3 will also rotate angle theta, like so. Okay. Let's go ahead and compute the elements now. Let me make sure that I can see that those elements at the bottom. Third step, project old onto new. I'm projecting the old I2 onto the new I3. What do I get? I lay my finger, in other words, I lay my finger along the new I3 vector, and project the old I2 vector, I'm going to get what? Cosine of theta. We know that the projection onto the new I3 from J is 0. But how about K? The old K vector is going to drop onto the backside. You see it? It's going to drop onto the backside of theta. If I drop it perpendicular, it's going to drop onto the backside of theta. So therefore, this is going to be what?
Negative sine.
Minus the sine, yeah? So this is going to be minus the sine of theta. Now some of you can say, all right, BZ, I've seen this enough. You don't have to show me anymore. I know this is going to be the sine theta, and this is going to be the cosine of theta. And of course, you would be right. So you can kind of use some tricks to make this go faster if you would like to do that. Go faster. So that's our second one that we derived. Okay. The third rotation is going to be about IB, which I can't get to show on it. So the aircraft has gone in the horizontal plane, the heading, it's rotated up to IB, and then the IB axis will rotate the wings. The J2 of the wings will become JB of the actual wing. J2 will become, or J3 will become actually JB, the right wing, and the aircraft will have this arbitrary attitude. And we will have been rotating, again, I've been rotating about the IB vector. The rate, phi dot, the rate is perpendicular to this plane. Here's the plane normal to IB, and that means the wing goes from 2 or 3, J2 and J3 are the same, to JB, and that's our final rotation. So we've gone through heading, pitch, and roll angle phi to get to our final orientation. So we have one more. All right, so let's do our third one. This task phi. Task psi was heading. Task theta was pitch. That was pitch, and now we're going to do task phi, which is roll angle. Okay. So we're going to look down what vector? We're going to be having our airplane, and what's the common vector? IB and I3, yeah? So I'm going to look down get it from where I'm at, that way. So I'm looking down IB, okay? I'm looking down the IB, it's going away from me, like this. So if I'm looking that way, then out the right wing, I'm going to see what? J. So I'll see J3, and I'm going to rotate that. Of course, I'm going to have K. This is going to be K3. And then I'm going to rotate through roll angle phi. We're just going to rotate through roll angle phi, and that's going to give me JB out the right wing. And of course, K vector is going to rotate. Now, K is rotating in that cockeyed plane up there. K is rotating in the cockeyed plane, but it's going to end up KB. And KB, of course, is defining down relative to me. Okay. Is your right brain working well enough to see that? So I have this angle phi, and I have this angle phi here. And now we can do the third step, which is to find into-body axes from the 3 system. And the first step we do is lay our fingers along the new I vector. Well, the I vector is going into the board. So what's the first row going to be?
1, 0, 0.
1, 0, 0. So the first row is going to be 1, 0, 0. And I can cheat, because I know tic-tac-toe says that these are going to be zeros also. So I can cheat a little bit. Then I lay my finger along the JB vector, which is new. So I lay my finger along the JB vector, and again, the first one, I is 0. The second one is going to be JB and J3, and that's going to be what?
Cosine.
Cosine of phi. And I lay my finger along JB again, and now I'll take the old k vector, and the k vector looks like it's going to project onto the front side. The k vector is going to project onto the front side like so. So this is going to be sine phi over here. Now you know what the last row is going to be, but let's go through it anyway. The last row, I put my finger along KB. Along KB, I project the old I vector onto it, gets 0. I project the old J vector onto it. Do you see how it's going to drop on the backside?
Yeah.
I'm not going to draw it because it'll take me into this matrix. But it's going to project onto the backside, so it's going to be minus sine B. And then the K3, KB is going to be cosine. Okay. So how can I clean this up now? How can I clean this up and find... I was going to tell you guys that finish this up. How am I going to find this? Well, let's go back and think of what we did. So how am I going to find this guy? Well, we started out... How did we start out? We did the first thing, we went from the V frame into the 2 frame. And I know that that's a function of heading angle psi. And we know what that is. So that's the first rotation. Then we went from the 2 frame into the 3 frame, and that was a function of pitch angle theta. So this is heading psi, and this is pitch angle, P-I-T, angle theta. And the last one we went from 2 or 3 into the body axis through roll angle phi. And this is going to be roll angle phi. Does this product equal, does that equal Cv2b? Absolutely. It does. Because if you were to take an arbitrary vector, let me move this over a little bit. Say you were taking an arbitrary vector. Let's just pick VK. Yesterday I used vector VK. Let's put VK over here. That's an arbitrary vector. Now what frame does it have to be in? This arbitrary vector has to be in what frame? It's got to be in the V frame. From 2. So this has to be in the V frame. Okay? This will take the vector in the V frame and express it. This will give me, this product will give me VK in the 2 frame. You see that? Now when I take VK in the 2 frame and multiply it by this, I'm going to get what? I'm going to get VK, comma, 3. And when I take VK, comma, 3 and put it here, I'm going to get VK, comma, B. Okay. So if I was going at God's speed, if God looked down on my airplane and saw me going at this speed in the VK, northeast down, and I wanted to know what my indicator, no air in the face, I would run through this coordinate transformation, and that would give me my wind in the face. So I could transform the velocity vector from any coordinate frame I want to using this product. Okay, yeah, Zach.
And we always do yaw, pitch, null.
Yeah, always, the order is crucial
Yeah.
in this. The order is crucial. So let's review that just for a second, because it is so crucial. So, all right, northeast down. Northeast down, okay? Always stays, this is my V frame, northeast down. I'm in an arbitrary attitude, like this, arbitrary, just pick one, okay? So we have to go backwards now. If I want to go to northeast down from here, I got to go backwards. So I'm going to roll minus my roll angle about IB until my wings are parallel to the horizontal plane. Then I'm going to go through the minus J vector, J2 vector, through the heading angle, minus theta, until my IB vector is in the horizontal plane. Then I'm going to rotate through kV, minus kV, my negative heading angle, until I'm lined up northeast down. So you go from any arbitrary attitude, reversing the angles, and get to, or frontwards, you'd start the airplane northeast down, take it through some heading angle, through some pitch angle, through some rotating angle, and get to your final position. Any arbitrary position. There's one catch. What if I start from here? Here's my northeast down. I'm starting here. Where am I going to roll my wings to get into a... I'm already in. My wings are already in the plane parallel to the horizontal plane. So no matter how I roll, my wings are already in a plane horizontal. I am screwed. So when you go straight up or straight down, the order procedure we chose breaks down. Won't work. So what's the bottom line? Do we throw this all away? No, we just tell our pilots, don't ever go straight up or straight down. If you ever do go straight up or straight down, what do we show them? A blank screen. Right? You show them a blank screen. Well, maybe you show them a white screen if they're going straight up and a black screen if they're going straight down. That'd be nice. But there is no, you can't show them pitch, angle, and roll if you're going straight up or straight down because your heading is undefined and your roll angle is undefined. All you know is your pitch is plus or minus 90 degrees. That's called gimbal lock. And we'll have a whole lecture on gimbal lock when we talk about quaternions next week. But it's a crucial flaw in this system that we've built together. But this is the system we have to live with. Zach brings up a good point. I didn't have to go, you know, I could have gone pitch, roll, heading. You could have gone a different angle. There's 9 different ways you could have gone to get to a final attitude. Right? And the space guys exercise no great pleasure in picking arbitrary ways to go from one satellite location to another one. I wish they would just use the same thing that pilots have picked, heading, pitch, yaw. But they'll use alpha 1, alpha 2, alpha 3. So their direction cosine matrices will look like this, but they'll do the same thing, but they'll all have different elements in it. Now this is going to be highlighted by your quiz or your readiness check that's due Friday, where you'll see that the vectors are kind of arbitrary that you pick, but you have to nail them down to get a unique answer. Good question. Okay, that's it.